Okay, here we're going to look specifically at properties and applications of logarithms. So before we can even get into using the properties, we need to refresh what those properties are. So first of all, we have the product property. Product property says that if you take the log of some product, then you can separate it with addition. Now notice my two bases were left the same, and so we can split them apart. Well, that also means if we have the log where our two bases are the same and we're adding them, we can reverse the property, which says we can write it as a single log, which would then be the multiplication. So when we're talking about properties, we are talking about flowing in both directions, okay? Either to what's called expand or to condense. Okay. Well, the same occurs with your quotient. So notice if you're taking the log of a quotient, it splits through subtraction and vice versa. So here the subtraction would be your expanded log, the division would be your condensed log. Your power rule works the same, okay, whereas here I'm taking the log of a power. Now the way that this works is that my power comes down in front. So my power right here, which is the little value, is going to move down in front through multiplication. And that's how we get n times the log of your value. Okay? Now some other properties that we have are that you need to remember the log of 10. So notice there's no base written. When there's no base written, it is assumed to be common log. Well, that gives you a 1. Same as if the base and what you're taking the log of are the same number, then you get a 1. We also have our product rule, or a product power combination, which says if the base of my exponent and the base of my log are the same, then whatever we were taking the log of ends up being the result. Okay? In other words, a to the log base a undoes itself. Okay? So there, we're making sure that your two bases, the exponential base and the logarithmic base, are exactly the same. If that's the case, then this undoes itself, and the only thing that's left is what you were taking the log of. Same for natural log. Natural log and e undo themselves, and here, when you take the natural log of e, you get 1. And we also have a version of the log. So notice I'm taking the log of an exponential. Again, because my two bases are the same, then what I'm taking the exponential of becomes your answer. So these are all the different properties that you may have to use depending on what you need to do with your logs. So here, this example says that you need to use your properties to expand. So this is your key word. We are going to expand the expression, and then you need to simplify any numerical expressions you end up having. Okay? So first things first, when we look at this right here would be your product rule. Therefore, when we expand, it means we have to add. So product rule means that we need to add your logs together. So this is going to become the log base 5 of the 125, and I'm going to add it to the log base 5 of x cubed. Now, there's a couple things that we need to look at here. First, this part right here is a numerical value. So here I need to actually do the math. The second part that we have to look at is that right here we have the power rule. So the power rule says that the power has to come down in front. So this right here has to move down in front through multiplication. So first things first, I have 5 to the something has to give me 125. Well, that is going to reduce to 3. So if we're looking at mini math, we are looking to simplify the log base 5 of 125. So we can simply rewrite that. That becomes 5 to the x equals 125. Change your bases. So 5 to the x is 5 cubed. Since my bases are the same, it means x equals 3. So therefore this is going to reduce to 3. So here this becomes 3 plus. And then I needed to pull the power down in front, so this becomes 3 log base 5 of x. Now since this is a variable, there is nothing else that I can do to simplify it. Therefore, I have expanded my value or my expression out as far as I can. Alright, so let's look at another one. So here I have the log base 3 of 9x plus 27y. So first, when I look at this first part, I can actually pull out a GCF. So here, I want to look just at here, and I want to identify the greatest common factor, because as it stands in this state, there's nothing I can do to expand that. So I need to find the greatest common factor, which in this case is 9. And I need to rewrite. So this is actually the log base 3 of 9 times x plus 3y. So this right here now is going to be my product rule, which says I need to add. So again, now I'm going to have my log base 3 of 9 plus my log base 3 of x plus 3y. Again, for this part here, this is my numerical piece. So here I need to do the math. So here I'm looking at that I need to simplify the following. Log base 3 of 9. So again, I can rewrite it. So here I've got 3 to the x equals 9. My 9 here can become 3 squared, so this is 3 to the x equals 3 squared. So because of this, we get that x equals 2. Therefore, the log base 3 of 9 has simplified down to 2. So this is 2 plus my log base 3 of x plus 3y. Now because this is a binomial expression, there is nothing I can do to simplify that further. Therefore, we are done. Okay, so this would be the answer that we were looking for as its complete expanded form. Alright, so now if we look at this, we have a log with inside a log. So this is what we need to look at first. So first we have to expand here. And then we can worry about looking at it as a whole to see if there's anything else for us to expand. So here I have the log of 100 times x cubed. So this right here is going to again be your product rule, which says we have to add. So this becomes the log of my log of 100 plus my log of x cubed. So this right here is our common log, which means it actually has a base of 10. So we can actually simplify that. So here we're looking to simplify your log base 10 of 100. So again, this is 10 to the x is equal to 100. 100 can change, so this becomes 10 to the x equals 10 squared. Therefore, it gives us that x is 2. And the other thing that we have is right here, we have a power, which says I need to take this 3 and it needs to shift down out in front. So what we have overall is we have the log of 2 plus the log, or 3 log of x. And again, because of this little plus sign right here, there's nothing else really that we can do, as well as since I still have this log function right here, it means that I am as simplified as far as I can go, and thus that would be your expanded result. Alright, so now I have the log base a to the 4th root of all this stuff inside, and I have to expand this out. So the first thing that I have to recall is I have to recall what my root says. So I need to recall that your root is the bottom, i.e. denominator, of the power. So I need to rewrite my radical into a power. So I need to rewrite my 4th root into a power, which is something raised to the 1/4. So this problem is actually going to be the log base a of my stuff on the inside, m to the 8, n to the 12, all over a to the 3rd, b to the 5th, and it is raised to a power of 1/4. So now that I've rewritten that, I need to start working on expanding. So here, again, I need to use my power rule, which says this 1/4 has to come down to the outside. So to start me off, I have that this is 1/4 log base a of my stuff, m to the 8th, n to the 12th, all over a to the 3rd, b to the 5th. So the biggest thing that you have to do is you must work from the what you would call outside in. Meaning, if you look at this, you can see that I have quotient, product, and power rules all being applied in here. So I need to know where to start. So I have to work from the outside in, meaning you need to look at it and you need to ask yourself, okay, what is the biggest rule that is being applied here? Well, I have stuff divided by stuff, which means the first thing I have to use here is the quotient rule. And remember, quotient says that we have to subtract. So this means I have my 1/4 is on the outside, and I now need to open a bracket so that I can start working with my material on the inside. So I'm going to have the log base A of my numerator, so this is m to the 8, n to the 12th, and I have to subtract the denominator. So this is going to be log base A of a to the 3rd, b to the 5th. Now the smartest thing to do is we now have two pieces. We have a product rule here and we have a product rule here. So you need to start with 1 and expand 1. We also need to remember we have this negative sign here, and that is going to play a big role to what happens in the back half. So right here we have a product, which means we also have a product over here. So we need to do them both individually. So this is going to be 1/4, open up your bracket. Remember, the product rule here says I have to add. So this is going to be the log base A of m to the 8 plus the log base A of n to the 12th. Then I have my subtraction sign. And in this case, I'm going to open a parentheses because I have the product on this side, which is the log base A of a to the 3rd plus the log base A of b to the 5th. Now, this subtraction sign is going to be distributed to the first term and to the second term. And so I would go through and I would distribute that first, which will drop these parentheses so that you have a clear playing field to work with. So this is going to be 1/4 times the log base A of m to the 8th plus the log base A of n to the 12th minus the log base A of a to the 3rd minus the log base A of b to the 5th, and close it up. Now, if you notice, I have power rules here, 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 and here. So I need to apply the power rule to all 4 of these components. So this is going to be my 1/4 times, and the power rule says each of these has to move down front. So that means the 12 has to move down front, the 3 moves, and the 5 moves. So we have to rewrite all of these to say 8 log base A of m plus 12 log base A of n minus 3 log base A of a minus 5 log base A of b. Now the last thing that has to happen is this 1/4, so this right here, now has to be distributed in to all 4 parts of your equation, as well as this right here is going to follow one of our rules. And that rule that says, as long as the log base and your exponent base, so if you remember, this would be like, say, to 1, as long as these are the same, log base a of a gives you 1 as a result. So what we have to remember is that this log base a of a equals 1. And so that is going to change and it's going to drop out. None of the rest of these are going to drop out because notice the base and what we're taking the log of are 2 different variables. A does not equal m, therefore they stay. So I have 8 times 1/4 is going to be the same as 8 over 4, which reduces to 2 log base a of m, plus 12 times 1/4 is the same as 12 over 4, which reduces to 3 log base a of n. Then I have to subtract. 3 times 1/4 is going to leave me with just 3/4. And then I need to subtract. 5 times 1/4 is going to leave me with 5 over 4 log base a of b. And that is the most expanded form that we have for this example. Okay. Well, now we have to go backwards. Here we're going to condense, which means we're going to take this expanded form and we're going to shrink it down into one form. Okay? So we have to look first. Notice my 2 bases are the same. If they were different, you could not do the problem. But because they're the same, we can go ahead and do it. And so here, because I have subtraction, this is going to apply my quotient rule. So the quotient rule says I'm going to have the log base 5. The first term is my numerator, so this is x. Then I'm dividing it by the second term. And here, this 2 has to then follow the power rule, which says it has to go back to being a power. So this becomes y squared. And you can put these in parentheses if you need to, or not, but essentially that's what we had to do. So we had to reverse these 2 rules in order to create that most condensed form. Let's look at one that's got a little bit more to it. So here I have something going on the outside, but then I have this stuff on the inside. So you need to do the inside first, which means the first thing that we're going to have to apply is your quotient rule. So I have 1/5, and then this is going to be the log base 7. Remember, this first term makes the numerator and the second term makes the denominator. So we have here, this is going to be your top, and here this one's going to be your bottom. So this is going to be x squared divided by PQ. And then this right here is going to follow your power rule, which says it has to go back to being a power. So it's going to come back over here into the power. And so this is going to become the log base 7, open a parenthesis, it's x squared over PQ to the 1/5. And the other thing that we can do with that is we can remember that our fractional powers also have meaning, where the top here is your power and the bottom here is your root, which means we can also rewrite this one to be the log base 7 for the 5th root of x squared over pq. Okay, so that is one way to condense that one down. So here let's look at a couple others, and notice there's a lot more that is in depth that we have to deal with. So first and foremost, right here we have a power rule, and the power rule is being applied just onto the x here, so this is going to come just right onto here, and so this is rewritten as the log base a of x to the 1/2, and then here is a power rule which gets applied to the y, so we have plus the log base a of y to the 4th, and then last we have a power rule here on the end which gets applied to this x. So this is minus log base a of x to the 3rd. So now I would start with my first two. So start from the left and work your way this way. So we're going to start at the left and move in that direction. So I'm going to look at just these first two terms, and I'm going to ignore the back half. And here I have the product rule. So the product rule says I am adding, which means I need to turn it to multiplication. So this becomes the log base a of x to the 1/2 y to the 4th, and then I've got minus log base a of x cubed. Last, this right here is going to be quotient rule. So the quotient rule says division, so I have the log base a. Remember, the first term makes the numerator, so x to the 1/2 y to the 4th divided by x to the 3rd. And so here there's a couple things that can happen. First, we can leave it alone, and we can recognize that x to the 1/2 is the same as a radical, and so you could rewrite it as being log base a of y to the 4th square root of x all over x cubed. Or you could play with the fact that we have two exponents here, and the exponents here say that in order to combine, you would have to combine through subtraction. So this would be the log base a of x to the 1/2 minus 3 y to the 4th. We would subtract 1/2 minus 3, and so here we would do the mini math. So mini math says we're looking at 1/2 minus 3. 3 is going to change, so we're going to have 1/2 minus. In order to get a 2 on the bottom means you got to multiply top and bottom by 2, so this becomes 6 over 2. So 1 minus 6 is going to give you a negative 5 over 2. And so here, that means this becomes the log base a. And remember, we don't like negatives, so we have to flip it. So this becomes y to the 4th over x to the 5/2. And then again, you could also write that in its radical form, which would say log base a of y to the 4th over Remember, the bottom tells you the root, the top tells you the power, so this would be the square root of x to the 5th. Okay. Now, to be perfectly honest, most people or most instructors would be looking for this first answer or the radical answer. And those would be the two that we would be looking for, and that's where we would want you to stop. And one of the reasons for that is because this answer down here leaves a radical on the bottom, and we're usually not too thrilled about that. And rationalizing your denominator is not necessarily something that you should have to do. And so therefore I would leave it as these two. But if you just simply want to play around with your exponents or play around with your fractions using some of those other rules, that's some of the things that you can do. Okay. Now, for this one, again, we have to kind of start from the outside in. So if we look at it, first things first, we have a power rule. So this one is power. And your power rule in this case is being applied to both of these two pieces. So here, this is telling us that we have the log of a squared b raised to the power of 2. So this becomes a to the 4th b squared. And then we have minus the log of 1 over b plus the log of 1 over a. So here I would go ahead and first work from the left side over. So here we have a quotient rule. So this is going to tell me that I have the log of a to the 4th b squared over 1 over b, and I have this to be plus then the log of 1 over a. So when I look at this, I need to reduce it. So your fraction rules say keep the top and change by flipping the reciprocal of the bottom. So this is going to become the log of a to the 4th b squared times b plus the log of 1 over a. Doing this multiplication gives me the log of a to the 4th b cubed plus the log of 1 over a. Now at this point we can apply the product rule. And so the product rule says that I have to multiply. So this is going to be the log of a to the 4th b cubed times 1 over a. So I can rewrite this, which tells me that I have the log of a to the 4th b cubed over a. So notice I have my a's are top to bottom. So I would do 4 minus 1 gives me the log of a cubed and b cubed. And there's nothing else to do, so this would be the end result of what we were looking for. And that would be the most condensed form that we have. Now, another rule that we have in place is called change of base. The change of base rule is used if you need to evaluate a log, but you do not have common. Okay? So common means you have a base other than 10. Okay, that's what common means. And it allows us to evaluate, and here you're actually going to, for the most part, be able to use your calculator. So change of base says you're going to change this into common. So that's your goal. So we are changing the log into a common log. That means we can use our calculator in order to find the answer. So here I have the log of 5.3, base 5.3 of 1700. So I'm going to use the change of base formula that says I can rewrite this to be the log of 1700 over the log of 5.3. Now because this is a decimal, that automatically tells you you cannot, or you shouldn't try solving it on your own. You should use your calculator. And so here, what you would do is you would do the top. So I would open a parentheses. You're going to hit your log button. You're going to type in your 1700. Close your parentheses, and we're dividing that by the bottom, which is the log of 5.3, and hit enter. And notice I'm asking to round to the nearest thousandths. So thousandths is 3 places. So this is going to be 4.460. Now, don't leave the 0 off, because then you've only rounded to the hundredth spot. So here we need to include the 0. So the answer here would be 4.460, and that would be the answer of your log. Okay. Alright, so here is just some more practice in being able to work with logs without using a calculator, which means you want exact answers. So here I've got evaluate log base 5 of 25 to the third. So the first thing that you would do is we would notice that here I have a power rule. So I would pull this down in front. So this becomes 3 log base 5 of 25. And then I would go ahead and simplify this piece. So this is going to become 5 to the x equals 25. So 5 to the x equals 5 squared. So remember x is 2, which means we have 3 times 2, which gives you 6. And this is our answer, 6. Again, we can evaluate over here. So remember, natural log and e undo each other. So here I have the natural log of e to the 1.5. So we can go ahead and apply this as your power rule, which says it comes down in front. And so here this is going to be 1.5 natural log of e minus log base 4 of 2. Natural log of e goes away, leaves me with 1.5 minus the log base 4 of 2. So here we got to simplify this part. So we have 4 to the x equals 2. So this is going to be 2 squared to the x equals 2 to the first. So I have 2x equals 1, so x equals 1/2. So what I really have here is I have 1.5 minus 1/2, which is going to give me 1 as an answer. Okay. Alright, so the very last thing that we can look at is using applications with your log ideas. And so here we have 3 different formulas that get used with logs. The first is pH of solution. The second is our Richter scale, so this is calculating your earthquake intensity. And then we have a decibel scale. This is your sound intensity. Both the Richter scale and the sound intensity scale are actually used by scientists today. So every time you hear on the on the news about an earthquake hitting somewhere and they say it had a Richter scale value of 7.0, well, what they did is they were able to measure the actual intensity of that earthquake and compare it to the intensity of what they call a zero earthquake, 0 level, which is basically I naught is 1. And then they can use that log formula in order to calculate the actual Richter number for that earthquake, and that's where those come from. That same principle is used with your sound intensity with one difference. We multiply by 10. So here's a couple problems that we can look at using these formulas. So first we have a certain brand of tomato juice has an H3O plus concentration of 3.6 times 10 to the negative 6 moles per liter. What is the pH of that brand? So we know that pH is the negative log of your concentration. So I just simply have to plug my concentration in. So this is the negative log, and my concentration was 3.16 times 10 to the negative 6. And then here I can use my calculator. So I'm going to take the negative log of 3.16. Now I need to do this 10 to the negative 6. So you see I've got this little 10 to the box. So I'm going to plug that in. That is your scientific notation on this particular calculator. And then here I'm going to take it to the negative 6 and close my parentheses. On other calculators you may see 10 to the caret and it may be listed above a button. Or you just simply would have to say multiply and then do 10 to the negative 6, and that would give you the same answer. So it depends on the calculator you're using. So again, this is just specific for my calculator. And so then you would hit enter and it gives you a result. And most pHs are rounded to the 10th. So we would say that this has a pH of 5.5. Now the next problem here says a 1994 Northridge, California earthquake measured 6.7 on the Richter scale. What was the intensity relative to the 0 level earthquake? So a couple things you need to know is that I naught is your 0 level, which equals 1. Okay. So here I'm also telling you that your R value was 6.7. So we need to plug that information in. So I know that 6.7 is equal to the log of my intensity over 1. Intensity is what we're looking for. So I need to solve this. So in order to solve this, I need to remember, if it's not written, this is common log of base 10. So I need to raise both of these by 10. So this is going to be 10 to the 6.7 equals 10 to the log of my intensity. So here, this part right here is what's going to go away. So this right here is going to go away using the rule. So this becomes a 1. So what we're left with is we are left with 10 to the 6.7 equals my intensity. And so then again, we need to use the calculator. So here, your calculator. So again, you could do 10 to the 6.7. Make sure you use the point, and that's going to give you your intensity. Okay? And so here we have that your intensity was 5011872.34. So essentially, we're looking at an intensity level of 5,011,872.34 times stronger than a zero-level earthquake. So okay, so that is actually what happened with that earthquake, and that is its intensity level. Okay, so here what you need to recall is that we use the rule a to the log base a of x equals x. That was the rule that we applied right here to our equation. Okay. Now the last one we have says the intensity of a cat's soft purring is measured to be 2.19 times 10 to the negative 11. Given that I naught equals 10 to the negative 12 watts per meter squared, what is the decibel level of the noise? So here I've got D is equal to 10 log of my intensity over the I naught. And in this case, I've told you that the intensity level is 2.19 times 10 to the negative 11. So this is 10 log of 2.19 times 10 to the negative 11 over an I naught value of 10 to the negative 12. So we would again use our calculator. So here I have 10 times my log of, I've got the top, 2.19 times 10 to the negative 11. Close my parenthesis, and I'm dividing that by 10 to the negative 12. And I get a decibel level of 13.404, and we would label that as being 13.404 decibels. Okay. So that's a kind of a snapshot into solving with logs and doing applications with logs. So as always, if you have any questions, please let me know. Otherwise, thanks, and see you next time.